Hey, what's up YouTube? In the previous video, I explained several techniques for making a character interact with water, the ground or foliage by generating an intersection map. This map could then be fed into a feedback shader to leave a trail behind, among other effects. In today's video, I want to follow up on that and show you how to approach it from the other direction. For example, how to make water have an effect on a character, like making it wet, dripping and so on. Alright, let's dive in. I'm going to attach a Niagara particle system component to the third-person character blueprint, specifically to the skeletal mesh component. This is important because it allows us to use Niagara skeletal mesh interface and let it get the skeletal mesh we want to sample from the component the Niagara system is attached to, if that makes sense. Now let's create an empty Niagara system, give it a fancy name, and set the system asset. Let's open it, get rid of that empty emitter, and create a minimal emitter instead. Switch it to GPU and make sure its bounds are large enough to avoid occlusion. Next, add a spawn rate module. 250 will do just fine. Set the particle color and size. Then create a new scratchpad module. Give it a name. Let's make some room. Add a skeletal mesh interface input. And from that input, get the skinned triangle data world space function. And for now, let's pick a random triangle. Use a getRandomInfo node. And set the particle position with the sampled position. Finally, configure the module. So set the skeletal mesh interface source mode to attach parent, provide a default and preview mesh. And this might prompt you to toggle CPU access on the mesh. Go ahead and do that. Set the skinning mode to preskin. Run the game and voila. Let's take it a step further. Let's set the particle initial velocity. Add a gravity force module. Add the required solve forces module. Then add a drag module. We don't need rotational drag though. And let's use a drag value of 2. Next, maybe a collision module, and let's try turning off the option to kill occluded particles. Okay, this is kinda cool, but if we want to draw some kind of wetness map on our character, spawning particles won't cut it. We'll need to work in UV space to actually draw a texture, right? So let's try something. For each particle, I'm going to generate a random UV. Let's make some room. Set a local 2D vector. Make a 2D vector. And generate a random float in a 0 to 1 range for both the X and Y components. And get that local UV parameter here. Good. Next, the skeletal mesh interface has this awesome getTriangleChord at UV function. So let's replace this with that. And it seems to work the same, except that it doesn't. Because if we think about it, what happens if a particle randomly picks a UV that doesn't correspond to any triangle? Well, in that case, this function outputs default values, so a 0 position. So we need to kill particles that pick invalid UVs. Simple enough, we can use the isValid output to drive the data instance alive parameter. Cool, but how is this any better? Well, let's think about it. Instead of generating a UV per particle, let's use a render target. For each pixel, we get its UV coordinate. We find the corresponding triangle coordinate, and with it, we sample the skin position's Z value. Then we test if that Z value is below the water Z, the ground Z, or whatever you want to test against. And if it's below, we draw that pixel as white. And that's pretty much the idea. So let's do that. And I'm actually going to step ahead and not only create a render target, but also a 2D grid at the emitter level. Give them both a name. Create a render target asset. Create a user parameter for the render target texture. Set it here. And assign the render target asset. Let's ensure the render target is set to rechannel 16 bits. Now, let's make a new Scratchpad module to set both the render target and grid 2D sizes. Give it a name. Create a render target input as well as a grid 2D input. And let's set the render target size and set the number of cells in that grid 2D. And while I'm at it, I'm going to create categories for these inputs because why not? Don't you love when things are organized? Configure the module's inputs. And double check that the render target is properly configured. Correct size, correct format. Great. Next, let's create a simulation stage to iterate on the 2D grid. Create another Scratchpad module. Let's call it Update Mask, whatever. Create a grid 2D input. And get the current grid cell UVs based on the execution index. And that part can be copy-pasted. Let's assume for now that the water Z is at 0 in world space. If the sampled position Z is below 0, I'm going to set a float in the 2D grid to 1, else 0. And to store a value in the 2D grid, assuming you're in a module called during a simulation stage that iterates on that grid, you just have to use the stack context namespace. Niagara will work its magic. But I'm also going to ensure the triangle coordinate at that UV is valid. Next, let's configure the module. The grid 2D input is the emitter grid 2D, and the skeletal mesh input could be configured the same way as before, but let's do something a little better. Let's create one at the emitter level and configure it just once. Attach parent, specify mesh, and use preskin. Next, set it here and here. The last step is to export the grid 2D float, the one computed in that simulation stage, which shall not remain nameless by the way, to the render target. So create a second simulation stage, still iterating on the grid 2D so we can easily grab that float. Create a new Scratchpad module, set its name. and add a render target to the input as well as a grid to the input. And since both the render target and grid 2D have the same size, I can use the execution index to get the render target index x and y from the grid 2D. And the value to write to that render target is that grid float value. Again, because this module is called during a simulation stage that iterates on a 2D grid, I can simply use the stack context namespace to get a parameter from the grid. I called it mask, so mask it is. Don't forget to configure the module and double check that everything is working. Meaning, let's go below 0 in Z in world space. Something's happening, but it's hard to tell. So let's better visualize what's going on. Here I used a simple material to draw the texture on the skeletal mesh using the emissive pin. Maybe turn off that particle system for now. Right, it seems to work, but it behaves a bit strangely. And the reason is simple. UE's skeletal mesh uses two materials to draw two sets of textures, and thus the mesh has overlapping UVs, which is problematic. A single UV coordinate may correspond to multiple triangle coordinates. So we have to edit that mesh and add a UV map with non-overlapping UVs. Fortunately, that's easy enough. Let's copy UE's mannequin asset. Drag the copied asset into the viewport. Go to Modeling Mode, UVs, and open the UV editor. Go to Channels, add a new channel, then copy the UV0 to UV1. Click Apply. Make sure we're on UV channel 1. Next, go to Layout and choose Repack UVs. Now, you might want to enable keep rotation to maintain the same tangent calculations. Tangents are derived from UV0, as you might know, so it's often useful to keep the same UV orientation in UV1. Anyway, click Accept. Get rid of that mesh. Update the Niagara system to use the new edited mesh. And switch the UV mapping index to 1. Display the render target using the second UV map in that material, and voila. What did I break? Oh, I forgot to update the third-person character blueprint. Duh. Ah, much better. See, any part of the mesh that is below 0 in Z is white. And that's not too impressive, right? At this point, you might say, well, just use a material on that skeletal mesh, sample the world Z, and create a mask. Simple. Well, yes, but you'd be missing the point. To create a persistent effect, like I'll discuss in a minute, this mask needs to be drawn into a render target for us to be able to fetch it the next frame. And when drawing into a render target, guess what? This corresponds to the render target's pixel coordinates. This absolute world position, actually reconstructed from the depth, only exists when rendering the scene, not when rendering into a render target, if that makes sense. And that's why to create such persistent effects, you have to go through more complex setups like the one I'm demonstrating. Now, there are a couple of things to mention here. First, you might see some kind of non-emissive lines here and there on the mesh. More on that in a minute. Second, you might wonder how that function actually works. And let's think about it. We have a UV coordinate in a 0 to 1 range, right? How do you actually find the triangle corresponding to that UV? It's what you may call a reverse lookup. And do we use a brute force approach, like loop over every triangle and see if that UV is inside the triangle's vertices UVs? That doesn't sound great, performance-wise, so it's always a good idea to double-check how things work under the hood. If we look at UE's source code and search for that getTriangleCore.uv function in the engine, we come across this function in the Niagara data interface skeletal mesh template.ush file. And this further leads us to the Niagara UV mapping utils.ush file. And it looks like it's using a quadtree as an acceleration structure for the reverse lookup. I won't dive into that, but it's at least a good sign for performance. It's not a brute force approach and it scales well with a triangle count. It's not free though, and it'd be interesting to see if we could precompute this reverse lookup once instead of doing it every tick. The UV at each texel is the same, so that triangle coordinate persists from frame to frame, right? There's no need to compute it over and over again. And actually, let's profile this. Now, things changed in UE 5.5. There used to be a performance button up here, but it's gone because apparently Niagara now uses a new virtual machine. However, you can of course still profile Niagara emitters. Just have to press play, open the Niagara debug window, and measure the average performance over a couple of frames. However, that doesn't seem to measure simulation stages. I'm not entirely sure though, I could be wrong. But in doubt, I'm going to do things differently. Let's simply briefly turn off the new virtual machine option to bring back the performance button while we measure the simulation stages. And for a 256 squared grid, it seems to be quite performant. Still, it'd be interesting to see if we can lower that cost. After all, this is just for one character, and you might want to scale up the system to support multiple skeletal meshes and so on. Anyway, third and final note, we'd want to make this effect persist and maybe fade it out over time. Let's focus on that for now. You might have noticed I used a Grid2D interface to do things in two different steps. First, I compute the wetness value, and then I output it to the render target. But I could have computed the value and output it to the render target in a single simulation stage. But I chose to do things this way because it allows me to create a feedback shader quite easily. See, I'm going to create a new simulation stage to iterate on the Grid2D, but only once upon simulation reset. I'm going to create a new scratchpad module to initialize this grid float to 0. Thus, once it's initialized, I can first access it in that other stage before setting it, and fade it out a little bit, meaning let's subtract the delta time multiplied by a fade speed control. And make sure it doesn't go negative. Let's do this in a local float called previous mask so everything makes sense. Rewire things. And while I'm at it, let's store this value in a local float called new mask. Get both and output the max of the two to set the grid float value. And voila! This creates a feedback loop and a persistent effect. Sweet! Now let's address the first issue, the pixelated black lines. In short, this happens due to the lack of padding when rendering this texture. Non-colored pixels outside the UV islands leak a bit around the UV edges. And there are several ways to solve this, like using the jump float algorithm and others. But I'm going to take a simpler brute force approach, and I'll do so because I'm going to pre-compute the reverse lookup texture, so the cost isn't necessarily a big worry. So I'm going to create another 2D grid and ensure it has the same number of cells as the other one. But first, give that 2D grid a unique name. And then it comes down to modifying this custom module and adding one more grid 2D input. And let's keep things organized and use categories. Gosh, I love this feature. Anyway, make sure to configure that new input and voila. Next, I'll set up a simulation stage, move it up here, give it a name, and make it iterate over the new 2D grid just once upon simulation reset. Then, you guessed it, create a new scratchpad module and name it. For now, I'll just get the UVs from the exec index. Make some room. And copy-paste this bit here to retrieve the skeletal mesh. And get the triangle coordinates from that UV. Now, the triangle coordinates consist of an integer for the triangle index and a vector for the triangle's barycentric coordinates. However, we can't store integers in grids. Let's give it a go still. Configure the inputs. See unsupported type in 32. So that integer will have to be stored as a float. And the convert node will do the trick. Get rid of that integer. Name that float. Stack context, good. The issue is that the 2D grid uses 16-bit floats by default, which seriously limits the range of integers it can store before causing problems. Now, you could use a bit packing algorithm akin to what Pivot Painter uses to store a 16-bit integer into a 16-bit float, but I'll choose a simpler solution for today's video. To fix this, I'll ensure the grid uses 32-bit floats. But even then, when dealing with indices, I'm not a fan of converting integers to floats and back. So instead, I'll pass the integer bits as they are without any conversion. And store the barycentric coordinate in that grid 2D as well. Once that's done, in that module, I'm going to create a new 2D grid input. Since I'm already using one, this new one will need a different name. From that new 2D grid, I'm going to retrieve the triangle index, stored as a float. reinterpret the float bits as integer bits, and also get the triangle's barycentric coordinates to form the triangle coordinate. This way I can eliminate the reverse lookup function and use the precomputed triangle coordinate instead. And as a validity check, based on that HLSL function, I know the baked triangle index will be negative if invalid, so I can just check that. Alright, moment of truth. Oh, what did I break? Oh, I added a new input to that module and forgot to configure it. It's always the same thing. So it must point to our new grid 2D that stores the precomputed triangle coordinates, right? Which, by the way, makes me think of something I should probably clarify. You might be wondering why I used the getPrevious functions to retrieve these 2D grid attributes, right? The float and the vector. Why not use the stack context namespace, like I've been doing until now? Well, the stack context, as the name suggests, is based on the context, specifically the simulation stage iterating on a specific 2D grid. So using the stack context, Niagara understands that you want to access the attributes of that 2D grid. But here I'm accessing the attributes of another 2D grid. These are not attributes stored in the 2D grid being iterated on in the simulation stage, right? Which is why I have to get the attributes manually via the appropriate get functions. Moreover, it's safe to do so because I configured both 2D grids to have the same number of cells. Hopefully that makes sense. Anyway, moment of truth once more. It works. Yay! And it seems to be 2 to 3 times faster. Meh, I'll take it. Now, onto adding padding, because precomputing this data has not fixed the black edges issue, right? Actually, I can say output the precomputed barycentric coordinates to a second render target to check that there's no padding at all. It involves a bit of gymnastics though, so let's take a look. Create a new simulation stage, iterate on the grid 2D that stores the triangle coordinates, create a new scratchpad module, add a render target and grid 2D inputs. I'll speed up the process. Set the render target value, same as before. Get the barycentric vector from the 2D grid. Use stack context, okay. Also get the triangle index, you'll see why in a second. Alright, let's duplicate this render target asset. Set it to RGBA 32 bits. Create a user parameter. Pick the asset. Assign the user parameter here, and let's use inherit user parameters. Finally, configure the grid 2D input. Double check that the render target still has the correct size and format. Okay. And it seems like I broke everything. Weird, huh? Well, I did this on purpose. This isn't very intuitive, but it's something I wanted to explain. See, this simulation stage iterates on the grid 2D, okay? This means that internally a buffer is created, a duplicate of that grid 2D, if you will. So you can both get and set the attributes of the grid at the same time. Which means the grid 2D is cleared of all attributes, so I need to carry them over. so carry the barycentric vector, and the triangle index integer as a float as well. And let's reuse the same validity mechanism to debug only valid triangles. So I'll need that HLSL bit again. And let's simply disable the setRenderTargetValue node if the test fails. Oh, and it's still broken. Oh, right. This execution behavior needs to be set to not on simulation reset, as to not conflict with this other simulation stage, which does the opposite. Notice we didn't have to worry about this kind of gymnastics before because this is a particular case. The attributes of that grid 2D are only set during the very first frame, so extra precaution needs to be taken when getting them afterward and ensuring they persist. Don't worry too much about this, you won't have to deal with it in most use cases. Anyway, it should work now. Yup. And there's indeed no padding in the baked triangle coordinates map. Therefore, any pixel outside the UV islands still doesn't sample a valid triangle coordinate, and thus we can't sample a position for that pixel, so it defaults to 0. Again, there are several ways to fix this. I'm just going to take the brute force approach. For each texel, I'll sample the triangle coordinate. If it's not valid, I'll iterate through the neighboring texels and retrieve the closest valid triangle coordinate to that texel. And this is how it translates to HLSL. First, I assume we won't be able to find a valid triangle index. I create 16 pixels of padding, which is enough for a 256 texture. Next, I get the UV from the 2D grid using the execution index. Then I get the cell count, from which I calculate the texel size. At this UV, I sample the triangle coordinate, and if it's valid, great, we are done. If not, we need to check the neighboring cells. Here I skip the pixel we've already checked, then I compute the neighboring UV, I sample the triangle coordinate again, and if it's valid and closer to the nearest valid triangle coordinate, I stir that UV. Finally, I sample the triangle coordinate at the closest UV, and voila. This adds padding, meaning pixels outside the UV islands are still considered valid UV coordinates for finding the triangle coordinates through the reverse lookup function. And thus, that translates to padding in the wetness map, right? This still isn't perfect, but there's only so much you can do with such a low resolution texture, and this is the worst case scenario. Lots of UV islands, plus black pixels versus white emissive pixels. Just the tiniest amount of bleed shows. Increasing the render target resolution, or adding extra padding during the UV repacking can help further solve this issue. And that's pretty much it. The fade effect is a bit boring though. And one thing you can easily add is controlling the fade speed based on the surface normal. I'll just swap those two sections, rewire things, store the Z normal in a local variable, and let's say remap it from 0 to 1 to 0 to 1 for now. Oh, and rewire this as well. And it seems to be working. Though the fade speed is now 0 on vertical surfaces, so let's tweak that. Let's set a minimum of 0.25, whatever. It's a bit more interesting, but still not great. Ideally, I'd like the wetness to run down the surface, almost like a fluid simulation. But that turned out to be much more complex than I expected, and for good reason. You see, first, to advex the wetness in 2D space, within the texture, there needs to be some mapping between the surface orientation in world space and its corresponding orientation in UV space. And that's nothing too complicated as long as you maintain the same UV orientation in UV1 as in UV0, which I mentioned earlier with the keep rotation option, right? This ensures the normal, binormal and tangent vectors, computed partly based on UV0, despite using the UV map 1, remain coherent even when using UV1. That means we can essentially just get a vector in world space. Then we do a dot product against the binormal to get the U component. And a dot product against the tangent to get the V component. Finally, we normalize the resulting 2D vector, and that's the world direction projected onto the surface in UV space. To visualize this, I created a new scratchpad module to temporarily replace the previous one, just for debugging purposes. In that module, I get the UVs from the execution index, just like before, but I also round the UVs to get truncated x and y indices for retrieving the precomputed triangle coordinates. This essentially creates 32 by 32 tiles in the render target, with each pixel in a tile sampling the same triangle coordinate. Using that triangle coordinate, I sample the skeletal mesh and project the gravity onto the mesh to get a direction in UV space, just like I explained earlier. From that unit 2D vector, I derive a simple rotation matrix to rotate the UVs in each tile and sample a basic debug arrow texture. I'm not sure if that makes sense, but it's kind of cool. See, this is a visualization of the gravity world direction projected onto the skeletal mesh surface. So it always points downward in world space, which results in it pointing in different directions in UV space. Neat. So say if we want to do some kind of fluid simulation on the skeletal mesh in 2D, or at least perform some form of advection in 2D, that correlates to a direction in world space, like gravity, we can do that. But it turns out that's just the tip of the iceberg. Eventually, you'll cross UV boundaries. And at this point, to correlate with the 3D surface in world space, what's advected in 2D needs to somehow jump to the appropriate UV coordinate when crossing a boundary. And there are two cases to consider. The first is when the adjacent surface is part of the same mesh and is connected. In this case, the UV border is simply a UV seam. The second case is when the adjacent surface is not part of the same mesh and is not connected. In this case, we need to find the closest surface and determine the corresponding UV position. This is doable and is what you might call an adjacency map. However, the method for generating such a map still eludes me. I figured the algorithm, but the implementation is what's bothering me. There's a lot of data to process on the mesh, lots of edges and vertices to query, many reverse lookups, and plenty of BVH queries for nearest neighbor searches. Plus, there are a lot of pixels to rasterize to generate the adjacency map, so a lot of processing to do. Unless I'm thinking this the wrong way, and I could be. I've already spent a week on it, and I feel like I'm just going in circles. I tried using Niagara, but I couldn't get a working solution. I tried geometry scripting, but I hit a dead end. Then I tried using geometry nodes in Blender, but reached another dead end. I even tried making a Python script in Blender, but the performance was abysmal, and that too seems like a dead end. I'm tempted to build a C++ tool in UE at this point, but honestly, I've already spent too much time going in circles, so I thought I'd at least make this video first. We'll see if I continue on this journey. For now, this is as good as I can make it. The way the wetness fades is pretty boring, but oh well. Now, there's still one more thing I need to mention. Remember, this used to be a good old particle effect. And what I'd like to do is spawn these particles only where the surface is wet, meaning where this mask is white. Well, at this point, that's actually pretty easy. We are already querying the triangle coordinates at the particle level in UV space, remember? So we just need to sample the wetness map. And kill the particle if the wetness at that UV doesn't meet a certain threshold. We may also want to prevent particles from spawning underwater if the wetness test passes. And voila! And I'll conclude this video the same way I kind of concluded the previous one. It's up to you to do what you want with this mask texture. If it's to drive a wetness value when diving into the water, well, maybe use a render target to lerp a roughness value, darken the albedo and so on for wet surfaces. And if it's to drive a dirt or mud layer, you could lerp a second material. There are all kinds of things to try, right? Go nuts! Voilà, that's it for today's video. I hope you liked it. Please consider leaving a like if you did and subscribing to the channel. If you want to support me and help fund this kind of research, files are available at your one reward on my Patreon. Thanks for watching, I'll see you in the next one. In the meantime, take care of yourself. Bye bye!